friends, we were discussing about severe plastic deformation. Okay. So, we will discuss couple of more processes where you can use this idea of severe plastic deformation. Okay. In that series, now today we will discuss about one of the process called accumulative roll bonding. Okay. Again all these SPD processes are very simple to implement. Okay. And the good thing about these processes are that you can use existing facilities, okay, which are usually available in the labs. For example, this is based on rolling process. So, already if rolling mill is there, you can easily adopt an SPD process like this using your rolling mill. Okay. So, what do we mean by this accumulative roll bonding? Okay. So, accumulation means you are continuously accumulating. Okay. Already I have told you that whenever we during conventional rolling, whenever we do rolling, okay, we are reducing the cross sectional area and of course, the length will increase. Usually there is not much deformation in the width direction. So, the deformation is only that thickness will be reduced, and because volume constancy has to be there, the length will increase, and slowly the thickness will keep on reducing and it will become the sheet will become very thin. Okay. So, for any structural application I need a certain thickness also to take the load. Okay. So, if I want to impose more strain, okay, the another way is that you do this kind of deformation, okay, and you can then do the stacking. Okay. So, as we said that length will increase. So, I can cut the sheet now and again put the one sheet over the another sheet, okay, and then again do the same rolling process. Okay. So, only issue which can arise here is that what will be the strength of bonding between the two sheets, okay, because the integrity of the sheet will depend on that what is the kind of bond which is forming between the two sheets. Okay. Usually we know that very quickly some oxide layers form on the surface, okay. So, and also during the rolling process there may be some lubricant which will be on the rolls. Okay. So, you have to have a very good preparation of the surface whenever you are doing the stacking sequence. Okay. First kind of do some mechanical removal of the material. Okay. Also basically you want to increase the roughness of the sheet, okay, so that it can create more area for the bonding, as well as there will be cleaning processes. Okay. So, it has its share of complexities in terms of the sample preparation or in terms of surface preparation. Okay. So, it is like conventional bonding is repeated continuously. However, when we are selecting the temperature of the rolling should be below the recrystallization temperature, okay, because the recrystallization temperature will relieve the accumulated strain. Okay. If there is any recrystallization during the first rolling process, then there will not be any accumulation of the strain in the material. Okay. So, recrystallization has to be avoided. So, usually the accumulative roll bonding we do at temperature lower than the recrystallization temperature for that material, and idea is to impose very high strain in the material, okay, through this process. Okay. And we kind of, because we are continuously repeating it, we are saying that there is not going to be much change in the geometrical property of the material. Geometry will more or less remain same after each cycle. And one of the microstructural feature of ARB will be like the microstructure will not be equiaxed. Okay. Already we have seen in ECAP, if you use BC route, okay, then after the complete cycle, the microstructure which was achieved was having a equiaxed microstructure or equiaxed grains in 3 dimension. Okay. But this is a rolling process and you are continuously rolling in one direction. Okay. So, the grains or the microstructure will not be, or grains will not be equiaxed here, but it will more like a pancake shape. Okay. Pancake you can, it is like pizza. Okay, so it will be like a shape of a pizza. So if you cut in the direction of the normal to that pizza surface, okay, then the grains will look elongated in this direction as well as perpendicular to rolling direction. Okay, whereas if you look from the top, it will be looking like a equiaxis structure. Okay, so this is a typical pancake shape, that from one direction the grain will be equiax, but from other two directions the grain will look elongated. So, the procedure already, as I told you, that surface of the two strips are treated, okay, and then you place it on one over another. In each cycle, typically the reduction which we want to achieve is more than 50%. Okay. So, 50% reduction in thickness will be there, okay, and that is to attain sufficient bonding. So, bonding between the two layer will be through the strain, okay, through the deformation. Okay. So, through the flow of material, okay, and they are going to kind of they will create a bond. And every time, as I told you, that the length will increase. So, you can section into two halves, put it back over one another, and again do the deformation process at a temperature lower than recrystallization temperature and with reduction more than 50%. Okay. So, this is a schematic diagram of the process. Okay. So, these were the two sheets, okay, which you have cleaned, did wire brushing and so on. Okay. So, actually we will start from here. You have done a rolling of the sheet. Okay. So, thickness has increased and the thickness has reduced, length has increased. Then you have cut the sheet into two halves. Okay. Then you have cleaned the sheet, okay, surface treatment, and then again staking, and then again it will be repeated. So, this whole cycle will be repeated, okay, every time, and in each case the thickness will be dependent on the amount of or the number of cycles which you are putting. So, we are already considering here that we are doing 50% reduction. Okay. So, it will be dependent on the number of cycle. Okay. So, if you have done 10 cycle, you can easily calculate what will be the thickness of the sheet. Okay. And where T naught is the initial thickness. Okay. And this is the relationship for the strain in the material, okay, which will also depend on the number of cycles. Okay. And again the relationship is assuming that you are giving 50% reduction every time. Okay. If it is not so, then you have to change this particular value. Okay. Half is taken from the idea that you are giving it 50% reduction in the thickness. Okay. So, simply if you these are all constant, if you do the mathematics here, ultimately you will get an expression like this, that epsilon will be dependent on number of cycle multiplied by 0.8. Okay. So, assuming if it is 50%, if you have you are putting 60%, you have to change the relationship accordingly. Okay. Now, as I told you that you are doing deformation, and through deformation the bonding is taking place. Okay. So, there is a very strong role of shear strain in the bonding as well as grain refinement in aluminum or in any material. Okay. So, and usually this particular technique is done without use of lubricant. Okay. So that you can have good roll bonding. What by avoiding lubricant, what you are doing is you are introducing lot of shear strain on the surface of the sheet which is coming in contact of the roll, and also there is a shear strain between the two layers. Okay. So, at that interface also there is large shear strain is acting, okay, as well as on the surface of the sheets, okay, which is coming in contact of the roll. And this shear strain actually kind of achieves the reduction in the grain size. Okay. So, there is a strong relationship between the shear strain. So, for example, this shows a shear strain diagram here, a graph here. Okay. So, the shear strain is more where you have second interface in the second cycle. Okay. Again the shear strain is increasing where you have the third cycle between the two interfaces. Okay. And wherever the shear strain is high, okay, you can see the thickness of grain. Okay. So, they have measured not the grain size, the what is, because you are continuously flattening the grains here through rolling process. So, what is the thickness of the grain, that is showing a sharp dip, okay, wherever the shear strain is very high. Okay. So, and continue again when the next shear strain cycle is there, again there is a dip. Okay. So, there is a, and this is the effect of the distance from the surface. So, only on the surfaces you will have high amount of shear strain, and there you will have very small thickness of the grain. As you go away from the surface, okay, where the shear strain effect will be small, again the thickness of the grain is increasing. Again there is a dip wherever the shear strain close to the surface is high. Okay. So, shear strain is being applied both through contact between the roll and the sheet, okay, which becomes the interface when you cut it and again stake it over one another, and there is also shear strain between the layers. Okay. This is an example of grain refinement in magnesium alloys. I am just kind of giving you is kind of a very brief overview of use of this particular technique in different materials. Okay. So, after these are comparison between two magnesium alloys here. So, AZ31 and AZ91. Okay. So, AZ31 has 3% aluminum, whereas AZ91 has 9% aluminum. So, aluminum content is increasing. Okay. Zinc content is same in both the case, which is 1%, and you can clearly see the effect of the alloying content on the microstructure. Okay. This is after first pass. Okay. And in this direction your strain is increasing. Okay. So, this is after fourth pass, and in this direction your aluminum content is increasing. Okay. And again this is your strain is increasing because this fourth pass, this first pass, and you can see clearly the effect of the strain on the microstructure. Okay. The refinement is increasing, and you can very clearly see the effect of aluminum content also, that as you are increasing the aluminum content, okay, the microstructure refinement is more. You can see that refinement in this case is more here. Okay. In fact, you are not able to even resolve the microstructure, whereas here I can see clearly the grains. However, there is more heterogeneity here. You can see there are some big grains are there, okay, and some very fine grain microstructure is there. Okay. So, there is a heterogeneity with more refinement. Okay. The reason maybe is because as aluminum is increasing, there will be more number of precipitates will be there, and this precipitate pin the grain boundaries. Okay. So, when you have recrystallization process, the recrystallization process have nucleation and the growth process. So, movement of grain boundary is required. So, if grain boundary is pinned, then it cannot grow. Okay. So, the grain size which you will achieve will be very fine. Okay. And if there is any maybe heterogeneous distribution of precipitate, maybe that is why you are getting heterogeneous microstructure here. Okay. Now, you can also interestingly with this particular process you can create multi layers. Okay. So, suppose you want to do a solid state or what we call as mechanical alloying. Okay. So, one alloying technique is that you take everything into liquid phase, okay, and then do the through phase transformation you create the alloy. Okay. But in that the amount of one material can go in another material depends upon the free energy or the basically phase diagram. Phase diagram decides that how much material will go into solid solution and so on. Okay. So, if you want to create have material where you want to introduce have more content of one alloying element into another, one way is to do mechanical alloying, and or you can also create multi layers. Okay. So, you can have kind of composite structure of metals, both can be metals, okay, and have multi layers of one alloy and another alloy. Okay. And the bonding between the two material will create this multi layer. Okay. So, this is an example of preparation of a multi-layer aluminum nickel composite here. So, the dark one, this one is aluminum, okay. Sorry, this one is aluminum, okay, and this one is, the dark one is nickel, okay. So, this is aluminum, this is nickel, okay. Nickel is harder compared to aluminum, okay. So, aluminum is able to flow, whereas nickel is showing the necking phenomena, okay. You can see a very nice necking is forming here, okay. Here already necking has taken place, and there is now aluminum is continuous here now, okay. So, nickel is divided into two parts, whereas in this case it is in the process of that necking. So, necking and fracture of nickel layer takes place, okay, and this nickel layer is actually cut by this shear bands, okay, and usually these shear bands are at 45 degree to the rolling direction. So, the fracturing takes place through this shear band formation, okay, and which is at 45 degree direction to the rolling, okay. And the heterogeneous distribution, as we have already seen earlier also, that there is a large shear strain heterogeneity in the material, okay, which is due to friction between roll and sample surfaces, okay. So, this create a very large strain wherever the interfaces are there, okay, and that is what is causing these shear bands and fracturing of nickel layer, okay. So, this is how you can create a aluminum nickel multi-layer composites, okay. This is another example of aluminum copper sandwich structure through ARB, okay. So, initially this is the primary sandwich. So, this light one is the copper and dark one is aluminum, okay. This is a SEM micrograph. So, you will have more in contrast, the copper should look bright and aluminum should look dark, okay, whereas earlier one was an optical micrograph. And again you can see the effect of copper being harder phase, okay. So, it is getting broken down, okay, and slowly you can see it is almost getting refined to very small sizes, okay, and having a kind of a continuous distribution throughout the aluminum matrix, okay. And again the same necking and fracturing is taking place in copper at different places. So, you can see that necking is there, okay, necking has started here, almost about to complete here, okay, and there is kind of break in the copper layer, okay. Here also you can see after first cycle itself there is a break in the copper layer. And the effect of this composite, if you can see on the strength. So, for pure copper the strength is around 240 megapascal, and for pure aluminum the strength is around 70 or 80 megapascal, okay. Aluminum, if you just do accumulated roll bonding in aluminum, okay, the strength increases to 300 megapascal. So, from here it can go up to here, okay. For aluminum copper composite the strength is even higher, okay. You can see that now the strength is around 360 megapascal. So, again there is an increase from 300 megapascal if you just compare with ARB in pure aluminum to ARB with aluminum and copper composite, okay. However, the total elongation is continuously decreasing in these all cases, okay, though there is a increase in the strength, which is a usual phenomena in all the SPD processes. We have seen that, okay. So, here also by having a composite like this you can achieve higher strength in the aluminum copper composite structure. So, again coming back to the same our story, okay, where we are saying that the severe plastic deformation processes actually though they increase the strength, okay, the ductility is reduced. So, in this case also ARB case also as number of cycles are increasing, okay, though the strength is increasing, okay, but the ductility of the material is going down, okay. So, this result is in IF steel, which is called interstitial free steel, okay. That means you have removed all the alloying element from the interstitial sides, okay. So, it is usually very soft materials. You can see that at no without ARB, okay, in normal condition the strength is maybe around 250 megapascal, okay, but with ARB you can increase it to 800 megapascal, but at the cost of reduction in elongation from around 60% to very low, maybe around 5% or so after 7 number of cycles. Okay. So, this is the usual story getting repeated in all SPD processes, that though the grain refinement achieve very high strength in the material, okay, but the ductility comes sharply with the introduction of strain in the material. Okay. Now, as already we have seen that this is also a very good technique to create composite, where the other part is maybe ceramic particles. For example, in this case silicon carbide particles are there. Okay. So, again when you are doing stacking, you can put this silicon carbide particle between 2 layers. Okay. So, they will get embedded in the matrix. Okay. So, this is of course the first one. Okay. Then you have second one is still you can very clearly see the effect of the stacking. Okay. They are in one all the silicon carbide particles are in one line. Okay. By fifth pass they are getting distributed, because as we already know that there are a lot of shear strains acting at the interfaces. Okay. So, the distribution and the breaking of this linear arrangement starts. Okay. By 8th cycle it is almost uniformly distributed throughout the matrix. Okay. So, a very nice method to make composite of some ceramic particle in the metal matrix. Okay. So, the material is aluminum 1050 and of course, silicon carbide is put in this. Okay. So, this ARB process can be also used for making, easily you can make composite of this kind. Okay. So, all these processes have lot of flexibility. Okay. You can create different type of materials, metal composite, metal ceramic composites. Okay. Also, by introducing in the same material multiple times, we are able to achieve very high strain and very fine grain microstructure, okay, which increases the strength, of course, at the cost of ductility. Okay. So, that balancing has to be done through microstructural control, and that is where your knowledge of metallurgy comes handy, that how you can do that to as we have already discussed, there are couple of approaches to increase the ductility. One is creation of bimodal structure, okay, or through that was another approach was there. Okay. So, my bimodal structure and these approaches are based on your metallurgical knowledge. Okay. So, that can be used for creating a material with good ductility also. Thank you.